could have tons of basic blocks and jump in between them. It doesn't really matter. So for like automated analysis, a function or basic blocks, a function has more cross references. A function exits a little bit different, but it doesn't really matter. So a basic block, since it has one input and one output, is kind of like, you can think of it as a math function. You have one thing goes in and one thing goes out, and there's like some type of transformation. So you take all these transformations, all these expressions from basic blocks, and you string them together, and that's your function. So that's kind of how we try to come up with these expressions and transformations to define functions, so that when we do the bottom up, we have like a formula for it. We don't have to analyze it all over again. And like I said, I don't care about self-modifying code. No, I don't care about analyzing I don't know, worms or whatever for vulnerabilities. I care about owning Microsoft. I care about Oracle. I care about the good stuff. So I'm going to show unbounded loops next. I'm going to cover my friend Matt, that's part of this project. He used to work doing static analysis. He had his own company, and then he sold it. One of the bugs he found was a client-side vulnerability in Trillian, in the RSS reader. And it's basically one of these unbounded loops. This is also very similar to what we saw with the MSRPC DCOM, like the blaster worm, where there was an unbounded loop looking for a backslash on the computer name. So this is what we use to find loops. We find something that's closed on itself, and there's a pointer. This pointer is being used for two things. It's being used to write out a value, and it's also being incremented. The exit from the loop is tainted byte comparison. So there's some user input involved in it. We track all tainted data, so we know if it's tainted or not. And that comparison that was used is being written to this pointer. So we know that user data is being written out to some location, it's being incremented, and that defines an unbounded loop. This is like an inline stir copy. Lots of compilers will do this instead of calling a library function. You save having to write stuff out onto the stack. You save having to do return, like all kinds of stuff. So this is an unbounded loop. It writes from the source to the destination. And once source is null or 0, then the expression is going to be 0, and it's going to exit from the while loop. So let me show you I can show you the Trillian vulnerability in IDA. So here's the entry to the loop. That's the top where it comes in. What it's doing here is there's a receive call. It's reading 1 byte at a time. This AL is the buffer is being held in. It's really hard to read sideways, but the buffer holds the 1 byte. It's being written to AL. Then AL is writing it to this combination of a base and an index pointer. EDI is going to be the base register, so that's the address of the buffer, and ESI is being incremented. So this is the thing that I was talking about, that what we're using to write with is being incremented. And then we come down here and we see that the value we're writing with is being used as a comparison to terminate the loop. So what's going on here is this loop is going to keep on receiving until it gets a new line. And it's writing it to EDI. If we trace up where EDI is coming from. EDI gets set here. This comes up from, this is being passed, this is an argument, it's a pointer. If we trace it back, this is where it's being passed. Just lost my place for a second. This is the stack buffer is part of the local stack for that function. It's the it's a local variable. I think it's like 800 bytes long or something. But so you're going to this function. You're passing a pointer to a stack variable. This is why you need to do inner function value tracking, because if we were only looking at that function, we wouldn't know if that was where that was coming from, if that was a certain size, or if it was being controlled somewhere else, or what it was about. That's why inner function value tracking is so important. So this is an exploitable vulnerability. It was a client-side attack. I don't know if this was reported to Trillian. They said that, I believe on this one, that they said that it was unlikely that someone would have a fake RSS server trying to exploit a client side. So it's been reported. I don't know if it's been fixed. You can go ahead and check your latest version of Trillian. Before I forget, let me... What's that? I don't think it really matters, right? They were told. You know, it's sometimes you tell vendors stuff, and if they don't want to fix it, they think it's not a problem. I don't know what to tell them. So this is the function, if you guys want to write down the address. I'd check, if you use Trillian, I would check it. So this is a simple vulnerability, and it was caught using binary static detection, and it catches bugs. Here's the something kind of similar. This is the MSRPC blaster. There was an overflow in the machine name. Basically, going into this function, all it wants to do is pull out the machine name. It knows that the machine name is terminated by backslash, so it's going to keep on writing into destination until it finds the backslash. So you can make that as big as you want, and you overflow a stack buffer. And I actually took this snippet from Mark Dowd's new book. It's an awesome book. If you don't have it, you should definitely check it out. Art of Software Security Assessment. There's all kinds of stuff in there for source code auditing, but a lot of it applies to binary auditing as well. It has really good sections on signed attacks, on integer. When things get stepped up to integer, comparisons between negatives and positives, comparing lots of comparison-based attacks on there. And they cover a lot of the vulnerabilities that they've discovered over the years, like the SSH challenge attack that one of them found. There's also the CRC32, the detach, the X2 bug. There's tons and tons of stuff on there. If you don't have that book, I would definitely get it. So bounded loops. Bounded loops means that there's some type of condition that's going to stop it. Whether it's let's say you're saying go through this loop 10 times or whatever. Just because it's bounded doesn't mean it's not vulnerable. There's been lots of vulnerabilities with like inline WSNN copy where people think that that function from Windows takes the number of bytes, but it takes the number of wide characters. So they put too many on there, and basically you create you can write twice as much to the output buffer as you intended. So the way that you look for this is you find that the closed loop, the jump back to the top, you look for pointers that are being written to and incremented. You see that there's a comparison with the input, and there's a variable, whether it's a register or on the stack or whatever it is, it's being incremented or decremented by a certain amount each time you go through the loop. So when you enter the loop and you're writing to this buffer, every time a buffer is created, we know the size of it. We like register like all malloc calls, all the stack allocations and whatnot. We know how much space there is. So we just go through this and just double check. Make sure that you can't write more than the buffer allows. So that's really quick coverage of what it does and what we've done so far. Like I said, it's still a proof of concept. Right now there's probably daily check-ins, daily changes. Been writing a lot of stuff for the emulator. I tried connecting earlier to pull down the latest build from SourceForge, and I had a problem with my internet. But if you catch me later, I'll have it on my laptop, and I can show you what's going on, or you can just pull it down yourself. So check it out. It's there. It's open source. You just look at the code. If you have any ideas, if you guys think I'm doing something wrong or something could be better, I would love the input. And is there any questions?
Keine Fragen?
Well, I guess I answered everyone's questions in the talk, huh?
Why did you choose to implement in C#? Sorry.
What's that?
Why did you choose to implement in C#?
I chose to implement in C# because Matt chose to implement in C#, and I was kind of forced to, I could say. But the real reason we did C# is because of Mono, because we could run it in Linux. It was sandboxed. The other choices we had was like a scripting language like Python or Ruby, or and I don't know. I kind of didn't want to do that. Go ahead.
Another question. Did you run into any bugs that changed when you started to observe them?
Any bugs that changed? Like
changed behavior. So you run the program like normal, it behaved differently than when you run it through your program.
Honestly, the code is so proof of concept that we're not at that level yet.
Okay, thank you.
Hi. I'm thinking about the stopping problem, and I was wondering if you've thought about how you're going to deal with things like recursion and possibly machine states that where you will not reach, or you cannot easily determine whether you will reach a stopping state.
Yeah.
Like
so yeah, there's definitely a halting problem, right? And what we're doing is basically a balance of kind of bang for buck. So we're saying, okay, we're going to reject these values because there's no way we can handle this many states. And we're going to miss stuff, right? That's just going to happen. I mean, it's either we do that and get some kind of results, or we try to come up with, God's own static reverse engineering tool, and it'll never happen. So If there's no more